So in the previous lecture, we started on grading vector. So let's finish some of the aspects about the grading vector, and then we're going to move on to another concept called directional derivative. All right? Yeah. So directional derivative. But first of all, here is a quick review of what grading vector is. Okay. And also, by the way, for the midterm, I think I mentioned in the previous lecture, the contents of the midterm is from Lecture 1 to Lecture 7, which are posted on the Connect. Okay. Essentially, it's assignment number 1, 2, 3. Okay. So grading vector is not part of the midterm. So you have well over a week to prepare, okay, and make sure you come here a little bit early for this next Thursday, right? Before this lecture, so we can hand out the papers and start maybe even a bit early than 3:30, so you have a little more time. Okay? Yeah. So what is a grading vector? First of all, the grading vector definition is very simple. Yes?
I just want to check for the exam, we don't have tutorials or anything?
No tutorial. Yeah, I'm not going to give you a midterm review or anything like that. Yeah. We cannot afford to lose any other lecture. Actually, this year we have only 22 lectures. Last year 23. So you're naturally one lecture short of last year. So that's not my style to give you a review on the things there. Yeah. But you probably get one in final. So anyway, if you have any questions, feel free to call by to ask. Right? Yeah. As I always said, you're not going to have formula sheets, no calculator. So if you feel there's any formula that think you need to remember, just write it down 10 times. Very often when students come into my office, my first question is, can you write down the formula? So if I see the hesitation that you can't even write down the formula, so what that means, you have to write it 10 times, okay? 10 times, maybe even 20. So the point is, there are not many formulas so far, okay, up to the midterm, but still, you need to remember. And if there's any integral skills that you need to refresh, go to your first year textbook, particularly like substitution rule, integral by parts, right? Those are very common integral skills. Yeah. Yes, there will be assignments, but the due date is not going to be next Friday anymore. So that'll be you'll have more due days. Okay? Yeah. Longer due days, more due days. Yeah. So don't worry, I will take things into consideration, right? Yeah. Okay. Here's a function. Then the definition of a grading vector is pretty simple. All you need to do is, if it's a function of a two variable, okay. If it's a function of a two variable, we know that this is a surface. Okay. And the grading vector is going to be just this one here, two partial derivative. It's a vector. It's going to be a vector in xy plane. If a function is three variable, then you have a vector, 3D vector. Okay, so that's the definition. It's very simple. If I ask you to calculate grading vector, but more important is to understand the physical meaning of grading vector. Now, I didn't prove this one, but I will prove today. However, I did mention about the physical meaning here. 2 points. One point is the grading vector always points in the direction of greatest increase, or the so-called steepest ascent, okay, in the function f. So basically, if you go along that direction pointed by this vector, then it's definitely the direction which corresponding to that direction is the greatest. It's causing the greatest increase of this function f. Okay. Yeah, that's one of the that's thing. This one here, you've got to remember this physical meaning here. Now, the second one here is the magnitude. The magnitude here, magnitude of this vector is actually basically the rate. It gives you the rate of increase. So it's, for example, if we have a single variable function, then we calculate the derivative, and we know that the physical meaning for this one is what? It's a slope, right? And slope, in terms of physical meaning, is the rate of change. Okay, it's the rate of change. So the grading vector, it's also a slope concept. Okay, it's a slope concept, but it's a vector though, huh? It's basically dealing with a slow concept in the 3D space. And the magnitude of that is basically just like this one. The magnitude of this, the rate of change. In this case, the rate of increase, because the vector always pointing is to the direction of the greatest increase. Okay? Yeah. So the next topic, once we finish this, when we go to the next topic today for the directional derivative, you'll see that there is a more general concept in terms of the slope. Okay? So we'll extend the concept. Okay? So a couple more things we want to finish about the grading vector is this. Okay? We actually touch upon this one here more or less. So first of all, I'll give you theorem. Okay. So if we have a function of two variables. Okay, the function two variable. So this is a surface, right? This surface. Then if we calculate the grading vector, like the formula giving at the top over there, and we can show that the grading vector is perpendicular to the level curves. Okay, to level curves. What is the level curve? Here's a surface. Level curve is you slice the surface with a plane z equal to c, right? So basically, level curve means this one. Okay, so you slice that with a plane z equal to c, you get a curve, and you project that curve into the xy plane, so you get a cluster of curve that's called the contour, right? So the grading vector is always perpendicular to the level curves. Okay, what does that mean is here is a level curve, for example. Here's another level curve. And if we're trying to calculate, let's say we have a point on this level curve, and we're trying to calculate the grading vector, then that grading vector is perpendicular to level curve. So this is hard to say. What does it mean by perpendicular? Well, that basically actually means is if you draw a tangent line at here, okay, then the grading vector is perpendicular to this tangent line. Okay, so that basically is what it means here. Okay, so that kind of naturally, basically, it's a second conclusion here. So the grading vector is perpendicular to the tangent line, okay, of this level curves. Okay, yeah. So if you say, okay, how about this point? Well, then you draw another tangent line at here, and then that grading vector del f at that location will be perpendicular to the tangent line at that location. Okay, so that's a fact. Okay. So that's for function of two variables here. Okay, if it's a function of three variables, okay, a function of three variables, then what we have here is, okay, the del f function of three variable. We cannot sketch that in 3D, but remember for function 3 variable, we can also visualize that using the so-called level surface. Basically, if you let w equal to c, we get a surface, right? We get a surface. So in this case, the grading vector will be perpendicular to this so-called level surfaces. Okay, f of x, y, z equal to c. Okay, yeah. Or just like the analogy, like the top one here, it's perpendicular to the tangent plane. Okay, to the tangent plane of the level, okay, surfaces. Okay, yeah. I'll explain this one in a little bit more. Actually, I'll show you the proof of this thing in here. Okay. So, what does that mean in here? Okay? So for this one here, so let me first of all let me explain a couple of the very simple things. I find often it's a little bit confusing sometimes. Let's just say first of all this. Okay, I give you z equal to f of xy. For example, x squared plus y squared. Okay, So I'll give you this expression here. Then you know that this is a what? This is a surface, right? It's actually a paraboloid, okay, like this. It's paraboloid. It's a surface. Okay? Yeah. So if you're going to calculate the grading vector del f, okay, this is del f here. So you get a vector of 2D vector, okay, 2D vector. So you are able to draw the 2D vectors in the xy plane, okay, as we said in the bullet number 1, and that grading vector will be perpendicular to level curves, and that grading vector will be tangent. Will be perpendicular to tangent lines of the level curve, right? Okay. So now watch carefully here. I'm going to just do it slightly different, okay? I'm going to move this one to the left side here. So I'm going to write it like this. So z minus this equal to 0. Is that right? Okay. So now you look at the left side here. I'm going to define it as a new function. So let's say I'm going to define it as w, x, y, z. Was that okay? Yeah? So nothing changed yet, just simple manipulation, right? So now this w here equal to 0 now, right? Equal to 0. So if I just look at this w of x, y, z, if I only look at this one here, so what is w of x, y, z? According to my definition, which is what? Z minus f of x, y, let's just say it's this function, which is z minus x squared minus y squared. That make sense, right? Yeah. So this is a function of how many variables? 3. So this is a function of 3 variables, and when you let w equal to 0, that's actually what we call, it's a level what? Surface, right? It's a level surface. If you let w equal to 1 or 2 or 3, it's another level surface. That makes sense, right? So now the difference is, if I want you to calculate is del w, okay? If the calculation is del w, it's not del f anymore, all right? If the calculation is del w, then you get essentially you get what? You get a vector, a 3D vector now, right? You get 3D vector. In this particular case, what's a 3D vector? This is a function. The 3D vector is negative 2x, negative 2y, and then 1, right? Partial w over x, partial w over y, and partial w over z, which is z and was 1 here, right? Okay? So for this particular one here, and as we said over here, right, over here, we said for function of 3 variables, then its gradient is perpendicular to what? To the level surface, this guy equal to c, right? So if I'm coming back here, let's just say I have a point x, okay, maybe there's a point, maybe it's 1, 1, 2. Okay, there's a point here. Okay, 1, 1, 2. So if it's a 1, 1, 2, that point satisfied to what? This point satisfies which one? Satisfies z minus x squared minus y squared equal to 0, right? Equal to 0. So basically, this point is on which level surface? It's on this level surface. Right? So this point is on this level surface, and if you put, and if you plug this point into this grading vector, and that grading vector will be perpendicular to which level surface? To this level surface. Okay? So now if I plug this point to that grading vector, what would I get? Then for this del w, it's what? It's negative 2, 1, right? 1. And this grading vector, according to my theory, it's perpendicular to which one? To the level surface, okay? To the level surface, z minus x squared minus y squared equal to 0. Okay? Yeah. Or, according to the theorem, this grading vector is also perpendicular to the tangent plane, okay, of this level surface here. Okay? So you see the meaning in here, right? Yeah. So when you're given one z equal to x squared plus y squared, sometimes we use it, okay, in a slightly different manner. Okay? Yeah, under different scenario, basically. All right? Yeah. Depends on what you're doing. Okay? So now I want to basically try to prove here why. So basically, I'll use this one here. I can prove both, but let's just show this number 2 here. Okay? Why this del f, okay, is perpendicular to the level surface or perpendicular to the tangent plane. Okay? So we're talking about grading vector, a 3D vector here. So now, essentially what we're proving here is this, right? We have a w equal to this. Yeah, so we have a function of 3 variables here. We're trying to prove, okay, so maybe I'll try to write it this way here. So given this, and we're trying to prove the del f at here is perpendicular to level surfaces. Okay? Yeah. Okay. So here's what we do. Because we're talking about level surface, so suppose that we have a one level surface. Okay. Assume we have a level surface, which means we let w equal to c, so that's a level surface. So for certain constant c, that is a one surface. Okay? Yeah. So for example, z minus x squared minus y squared, that's a level surface, right? Okay? And now, let's assume, I'll draw an illustration in here. So suppose that this is a level surface we're looking at. Okay? This is a level surface. That's the surface for this one. Okay? So then we're going to also assume this. Okay? So then I'm going to assume, assume a curve. Okay? We have a curve in the level surface. So you have a surface, you can draw basically any kind of a curve right inside this surface. Okay? Yeah. So let's suppose that this is our this is our r of t at here. Okay? This is r of t. Okay, C. Okay, that's a curve C. Okay, so now let's try, let's do this one here. So based on this level surface here, we're going to take, we're going to take a time derivative, of both sides of here. Now, you got to remember one thing here, because this curve, we assume this curve is in the plane, or is on the plane, on the surface. So assume this one is on the surface. Okay? If it is on the surface, so that means what? That means if I substitute the coordinates, any coordinates on the curve C into this surface equation, so basically sub here, 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 it should satisfy this level surface expression. That makes sense? Right? So basically, which means f x of t, y of t, and z of t equal to c. Okay? Now, so the curve is on the surface. So any points on the curve, the coordinates of the point, is going to be on the surface. Now we're going to take derivative, because this is going to be a function of t. So we can take derivative of both sides, with respect to t. Both sides t. And this is a constant, so that derivative is going to be 0, right? Going to be 0. And this side here, this is actually, we're going to use what? We're going to use there's two rules, chain. There's going to be a chain rule here, right? There's going to be a chain rule. So what does this side here give us? It should give us what? Partial f over partial x and times dx dt plus partial f over partial y dy over dt plus partial f over partial z and dz over dt. Okay? Yeah. So if you look at this one right here, okay, if you look at this, okay, then I'm going to rewrite this expression using a vector dot product. So one vector dot another one here. Okay? So the first vector is going to be and the second one is okay, does that make sense? Okay. So if you expand this dot product, you get back to this equal sign here, right? This expression. Okay? Now, you look at this dot product. What's the first one here? What's this? The del f, right? The grading vector. What's this one here? What's this? This is r of t is this. So this one is actually the derivative of this. Exactly, right? So basically the grading vector is dot the derivative of the parametric equation for the vector function for the curve, for arbitrary curve. Okay? Because you have infinite curves, right, on the plane. So that's arbitrary. So this guy dot this equal to 0. So according to dot product, what's the relationship between this vector and this vector? Huh? Perpendicular. Somebody said parallel. No. So this is this is a perpendicular to this derivative of this curve. And what is the derivative curve actually? Tangent, right? It's a tangent vector, right? So this is a tangent vector. Okay? So if you're based on this relationship here, let's go back to this drawing in here. Okay? Remember, here is an arbitrary curve I draw here. So I can draw any other curves maybe like this, right? They can all be represented using a vector function like this. And it doesn't matter which curve you draw here, they are all going to satisfy this relationship. The grading vector will be perpendicular to the derivative of that curve. So, which means if I pick an arbitrary curve right here, let's say pick this point here, maybe pick this point, then this point is on this curve, and I can draw a tangent vector, right? I can draw a tangent vector at this point to this curve, and I can draw another tangent vector to this curve at this point. That makes sense? And it doesn't matter which tangent vector you draw, that del f, the grading vector at this location is what? Is always perpendicular to the tangent vector here. Okay? So now you tell me, what kind of thing contains all of the tangent vectors at that location here? So maybe you will have infinite tangent vectors at this location P. But you do have one thing that contains all the tangent vector, which is a plane, a tangent plane, exactly. So you draw a tangent plane at here, okay? So that tangent plane contains all the tangent vectors at the location P. And best of all, the normal vector to the tangent plane is del f. That makes sense? That basically proved what that bullet number 2 there. Okay? Yeah. So del f is perpendicular to the tangent plane. Yeah. Okay, so that actually naturally brings us to the question right here. In the past, in the previous lecture, we actually draw the conclusion. We said we can approximate a surface using a tangent plane around certain point, right? We actually, basically, if you recall that, okay, for a z equal to f of x, y at here, right? For z equal to f, this surface, okay, I'll give you a slightly different surface later, but for this one here, we said we can use a plane to approximate this surface. So that plane is what? That plane is, we can use a plane. So at a certain point, x naught, y naught, so we can use a plane f of x naught, z naught, okay, equal plus, okay, fx, okay, at this x naught, y naught location, x minus x naught, plus fy, x naught, y naught, y minus y naught. And then we can just let z equal to this. Okay? Yeah. So we use this one, okay, which is a plane, okay, to approximate, okay, z equal to f of xy. Okay? Yeah, f of xy here. Okay? Now, if you recall in the first lecture, you probably wonder, is that a plane? Yes, it is, right? I had to rewrite that one to make it more look like a plane. What do? You can basically move all of this thing here to the same side. So you end up with fx, okay, at this location, x minus x naught, okay, plus fy, okay, x naught, y naught, okay, y minus y naught. Okay. Before it dies out. Good. Plus z minus f of x naught, y naught equal to 0. Okay? Yeah. Okay. See, look at it, right? Look at this one here. What's the coefficients at here? The coefficients for this term is this. For this one is this. For this one is 1, right? It's 1. Oh, sorry, it's negative, right? Negative, negative. Okay? Negative, negative. Okay? And what's the coefficient at here? The coefficient is actually, which is what? Which is, I think I just did it here. No, I guess, you're right. But the coefficient is basically negative fx, negative fy, and 1. Right? That's the coefficient. And this coefficient, as a matter of fact, happen to be the del w, and w equal to this. Can you see that? So we're using a plane to approximate the surface. How do we get the plane equation then? So this backs basically to lecture number 2. When you're creating a plane equation, what do you need? You need a point on the plane, and you need a vector perpendicular to the plane. And that vector perpendicular to the plane is the coefficient, the component of the vector is placed at here, here, here. And what we just proved is the grading vector is perpendicular to the plane. So naturally, you can just simply take the grading vector as here. right? So basically, if there's a question asked is, here's a surface. Can you find me a tangent plane to this surface at a certain point? Then what do? You already have a certain point already. Then all you need to do is to find out the tangent, to find out the grading vector at that point, and then use the plane equation to create the tangent plane. Okay? Yeah. So I'll give you an example here. Okay? But this is a slightly different though. So here's a surface. Okay, here's surface. And try to find a tangent plane at 2, 1, 1. Okay, at 2, 1, 1. So if you look at this one here, I think your immediate impression is, how come it's different now, right? Remember the previous one that we've always seen is, oh, here's a surface, right? But in this case here, there's x squared plus y squared minus z squared to 4. It's not in the format z equal to something, right? It's not in the format z equal to something, okay? Yeah. But it's still a plane. This is basically what we call, it's an implicit, okay, implicit function. Essentially, you are not getting an explicit form of expression for z. Okay, it's embedded, it's implicit, so it's kind of embedded in this expression here. Okay, why is it still surface? Because, you know, this is essentially satisfy the format f of x, y, z equal to c. You see, right? This satisfies this f of x, y, z equals c. And we know that this one describes a level surface. It's a surface. Okay? So this is a surface. Okay? Yeah. So you need to get rid of the doubt that this is not a surface. Okay, it is a surface. So now, what will be a tangent plane for this surface at this point? So your first step is actually what you need to do is you need to look at whether this point is on the surface or not. Okay? Yeah. Well, that's very easy to verify. So what do? You basically plugging this point into the left side, what do you get? You get 4 plus 1 minus 1 equal to 4. So that's a check, right? So that point is on that surface, on the level surface. Then the next step, what you need to do is now is you're trying to create a plane. So you already have a point 2, 1, 1. So you already have this x minus x naught, which is minus 2. So all you need is a coefficient now, or all you need is a perpendicular vector to this plane, right? That's all you need. Okay? And as we just proved, the grading vector is perpendicular to the tangent plane. And the grading vector here, right, if you define, let's say, if I let w equal to x squared plus y squared plus z squared. Okay? Yeah. Then the grading vector is del w. Okay? Del w equal to, what is it equal to? It's 2x, 2y, and this is not plus, this is minus. Okay? And then what? Negative 2z. Okay? That's the grading vector. This is the grading vector arbitrary, so general. You don't need a general, you need the grading vector at which location? At this location here. Okay? So the del W at 2, 1, 1, okay? So plugging x equal to 2, 4, y equal to 1, 2, z equal to 1, negative 2. That's the Grading vector at the location. Okay? And this is your A, this is a B, and this is a C. And then plug it in, you have your tangent plane. Right? Yeah. Is that clear? Yeah. So, somebody say no? Who said no? Yeah, why is that?
It's good to me, I have a question.
Yeah.
With the fact that our original plane, our original surface, and they added equal 4 instead of equal 0, that doesn't make any difference in getting the W?
Yes, it does make a difference. Well, okay. The question actually should be twofold. In terms of calculating del W, it probably won't make any difference. Because why? This is a constant here, right? So this is the constant when you calculate del W. And actually, you know what? More precisely, when I define the W, I should define it as this, like this. Okay, minus 4. Okay, yeah, minus 4. So you see, when you calculate del W, the minus was a constant, so that doesn't make any difference at all, right? Yeah. But it doesn't make differences if this is 0 or this is 1. Then if you change this one here, that point is not going to be on that surface anymore. You see what I'm saying? Yeah. So that the question probably had to change the point at here. Yeah. Yes. Good? Yeah. Okay. So essentially, this is more or less what's got involved for grading vector, right? In terms of calculation, pretty simple. There's nothing that, basically nothing there. It's just 3 partial derivative or 2 partial derivative, right? Yeah. But understanding the physical meaning, it's important, okay? Yeah. So now let's move on to the next topic, okay? Directional derivative. So this is another interesting topic right here. Again, just like a grading vector, it's when you look at, if I gave you the final formula, you'll say it's very easy. Okay, everybody can do that. Again, it's the way to understand the meaning behind the formula. All right? Yeah. So I think everybody knows derivative. Now the problem here we add directional derivative. Okay. So that's basically the key in here. So let me start from the simple case. Now, if I have a curve like this, right? This is basically the 2D case here. So how do I get the derivative, or how do I get the slope? And if you remember that, so the slope is df over dx, and that's taking the limit. Okay, the limit is f x plus delta x minus f of x, and divided by delta x, and delta x goes to 0. Right? That's how you calculate derivative. Okay? Yeah. Now I want you to understand this way here. Okay? Understand this. This derivative right here, you see this one here, this is x plus delta x. Okay? So in other words, let's say this is x location, maybe this is current location A here. Then when you say plus delta x, consider yourself as you are going in the direction of increase in the positive x axis. So you're going to increase yourself to here. Okay, to here. So basically, consider yourself in a motion kinetic. So you're increasing, you're walking in that direction. Okay, you're walking in that direction. When you walk in a direction, okay, there is a change f, there's original value, then you calculate this, you get the slope, or you get the derivative. That makes sense? Okay? Yeah. So for this particular case, this slope, okay, is actually what? Is actually a positive value, right? It's positive value. So now, if the other way around, if your A is going to be decreasing, if you're not walking to that direction, if you're going to this direction here, okay? Guess what? Well, okay, hang on a second. So let's say you're walking this direction. The slope is positive. Okay, the slope is positive. If the slope is positive, what does that mean? When you're going from here to here, that means there's going to be what? An increase for the function y, right? Yeah. So in other words, remember what I said. You're basically walking in the direction that will cause an increase for the function f. Okay? But in this particular, if I walk in this direction, okay, if I go this direction here, as you can naturally see, that there's going to be what? There's going to be a decrease in the function f. So that's the slope, we'll call it, basically it's going to be a negative value. Is that okay? So I'm kind of extending the concept of slope at here, okay? So it's not just the one k at here. I'm kind of extending the concept by taking into the direction of the changes, which direction you're going to walk, all right? Yeah. So that is essentially the whole idea of a directional derivative. So now let me extend this to the 3D concept here. Okay, so let's see in 3D. So then I'm gonna draw some arbitrary surface at here. Okay. So let's just say I have a surface. Okay. Yeah. So here's a surface. Here is one particular point, okay, in the xy plane. So this surface, let's just say, is z equal to f of xy, for example. Okay? Yeah. Now, if this is the point at here, maybe this is x naught and y naught point, right? Yeah. So at this point, there is a corresponding location on the surface. Okay? On the surface. Okay? So imagine yourself with this. So here, this is one stick magnet here. Okay? Yeah. And then there is another stick magnet over here. Okay? Yeah. So this is A and this is B. So the stick magnet A is going to be controlled by B as B is moving, and the A is going to move. Is that okay? Yeah. So now, so let's say if this B is going to move, okay, in, let's say in this direction, okay, an arbitrary direction here. Okay? Yeah. So then imagine this. If it's keep walking like this and the A is also moving or being controlled by B at the same time, so what's the commonality between A and B? So A and B always actually in the same plane, right? In the same plane. So essentially you got yourself a plane here. And that plane contains, right, this one. Right? This is a plane here. Okay? Now. And what about the curve traced out by this stickman A as the B is walking? That's going to be what? That's going to be in the intersection between this plane and this surface. Make sense? So if I plot it, and it's not very accurate, but maybe it's going to be a curve like this. Right? Maybe it's going to be curved like this. Okay? Yeah. So then, here comes the natural question now, right? As a natural question. So as the stickman B is walking in this direction, how does this rate of change in terms of the value at this stickman A there? In other words, how will the change in the function f as B is walking in this direction? That makes sense, right? So basically the question here is, right? So what is the rate of change in f as this B moving in a direction, right? In the direction. So we're talking about the direction. So I think I better use a mathematical symbol here to represent that. So if this is the direction, I'm going to use a U hat to represent that direction. Is that okay? Right? So I'll use this one here. So that's basically the question in here. That's very natural, right? Maybe it's going to increase, or maybe it's going to decrease, right? Who knows? Okay? But there's going to be a rate of change in this up and downs for this stickman A there, right? Yeah. So this question basically is asking us to do this so-called directional derivative. Okay? Directional derivative. Derivative is the concept of rate of change. And direction is this direction right here. Okay? Yeah. So to calculate this directional derivative, so we have to get used to this concept here, right? I'm going to use this concept. I'm going to define the directional walking as a so-called positive displacement, positive S. Okay? Positive S. Okay? Because this is not a conventional XY plane anymore. So you're not just changing in the positive X direction or the negative X direction. You're actually changing in 3D space in the direction you had. So I'm going to use this positive S. So that positive S is more or less like the previous positive X. Okay? Yeah. So if I look at this one here and asking us the rate of a change, basically, in other words, if we forget about the grading vectors or directional derivatives, and we just understand that there is a curve being traced out, right? There's a curve being traced out. And if you're asking what's the rate of change in that, actually it's what? It's the rate of change corresponding to this curve here, right? Because that stickman A is going to walk around this curve. So essentially what we're trying to look at here is what's the slope of this curve? That'll be the rate of change, right? What's the slope of the curve? So slope of a curve, so let's do this, right? I'm going to draw another one in here. I'm going to draw a positive z-axis and then positive s-axis. Okay? So we're talking about slope. And I better redraw that curve in a certain coordinate system to look at the slope. That makes sense, right? When you draw the coordinate system, your coordinate system is not drawn arbitrarily. You have to draw it like this. Because your positive S cannot be drawn this way here, okay? Because if you look at it from front, and it's always this way, okay? So here's a Z, here's a positive S, okay? So now if I look at this one here, look at this one. This is a Z, okay? This is Z, and this is S, okay? This is S. So now you tell me which direction. So I'm going to draw this just to make it fine here. I'm going to draw this like this, okay? Here is the green color, and here is the red color. Okay, here's the red color. So if I'm going to redraw that curve in this ZS plane, where's the green part? Where's that the red part? Red is on the left. Yes. Good. That makes sense? So, or maybe the last question is, which direction? This is the plane here. Which direction are you gonna look at from here, or are you gonna look at from here? So basically, which side do you want to look at it, so that you have this orientation of the axis on the left. That's correct. So if I look at that way there, that means my green color is over here. It's not exactly at that point. Well, anyway, just maybe something like this. Does that make sense? Who said I don't get it? Take a second look at this, if it makes sense or not, right? It's all about the direction. And now this concept of directional walking. It's the slope or the derivative associated with the direction. Okay? So you're walking in this direction. That's the positive s direction. And there's a curve traced out along the surface. And we're going to look at the curve in the z positive s plane. And according to the right current orientation, and this is basically this, right? This is this. So if I look at this one here, and then if this is the point, B at here, okay? This is point B. Then apparently, as point B is walking in the positive s direction, you look at this curve, what would you expect? You would expect a positive or negative derivative. Positive. See, that's basically, you're going to get the directional derivative, which is a positive value. Or in other words, it's an increasing. It's a rate of increase, right? In this case, you're going to get a rate of increase, okay, in f, okay, as you're walking in u hat, okay, as you walk in u hat, okay, yeah. Okay, so if you can understand this one now, this is basically the directional derivative. Now I'm going to give you the formula, okay, and in terms of how do we calculate this directional derivative, right? So definition and the notation. Okay? Yeah. Okay, so first of all, definite notation-wise, now suppose that, let's see, I have a function f, okay, and then there is also a p0 point, okay, so that point p0, okay, or the b over there, okay, and then we have also a direction of walking, okay, u hat, okay. So let's just say u hat is a unit vector. It's in the xy plane. So maybe it's we can denote that as a I hat plus b and g hat. All right. So that's the direction of walking. Okay. Or direction for change. Okay. Then the directional derivative. Okay. Then the directional derivative is this. It's a df over ds. So you see, it's all coming together now. So if it's xy plane, what's the slope? df over dx, right? Right now you're walking in this positive s direction, or the u direction, okay? The positive displacement. There's a positive displacement s, and it's going to be the ds, right? That's ds, okay? So in terms of symbol-wise, we are going to use a subscript indicating u hat as the direction you're walking. So there is a displacement change in the u hat direction, okay, in u hat direction. At which point? At this P naught point. Okay? So this is basically the notation. Okay? For directional derivative, I'll call it DD for this directional derivative. Okay? Yeah, that's the notation. And as you probably will see in some other textbook, you have probably will see this kind of notation. So D U hat F at P naught. So this capital D here is a differential. Basically, it's a derivative operator. Okay, taking derivative with respect to the F along the direction of U hat at the point P naught location. Okay, so that's notation wise. What are the definitions? How do we calculate this one here? So basically, this partial F, dF over ds. Okay, I'll rewrite that at P naught. Okay, that equal to this. Okay, equal to a certain limit. Okay, H to 0, H F. X naught plus AH, Y naught plus BH, minus F of X naught, Y naught. Okay? That's the definition. So let's take a look at this definition here, if that makes sense or not. Okay? Directional derivative, just like the slope, as you can see from here, it's actually a scalar quantity. Okay? You get a derivative scalar quantity. So what does that mean? Here, at the top here, your starting point is x naught, y naught. And then what did you do? You're walking in the direction of u hat. So, walking in the direction of u hat. Okay? How much did you walk? You walked a very small distance. So how do I indicate that? Basically, you walked by how much? From here to here, up to this location maybe. Basically, you'll just walk to HA and HB, like this kind of location, right? From here to here. Okay? Only a scale of that even, right? It's a very small quantity H. So that basically means along the x naught direction, there is a change A multiplied by H. Along the y direction, there is a B, and there is a B, H times B change. Okay? So there's all the limit kind of concept here. Right? That's how you calculate the directional derivative. Now this is probably, you're not going to use this to calculate directional derivative, but you're going to use this one here. I'll prove this to you one day. So you will use this to calculate this. There we go. Okay? Del F dot U hat. Okay? And del F at the P naught location, the dot. Okay? So we're talking about directional derivative at a certain location. So here is what you use. Del F dot U hat. That's pretty simple, right? That's pretty simple. I'll prove this to you, and we'll explain more meanings out of here. So del F dot U hat. What is del F? It's the grading vector. What's U hat? U hat is the direction you're walking. So the gradient dot the U hat. So before we move on, just a quick, we'll use this one here. What is the physical, what's the geometrical meaning of a dot product? It's particularly when you're using a vector dot a unit vector. What do you get? Projection. You get the length of the projection in that direction. So forget about the directional derivative. Just looking at this dot product here, what do you get? You get this dot the U hat. You actually get the projection of the grading vector in which direction? In the U hat direction, right? Okay. So let me prove this one. Okay, just quickly prove. Pretty quick. Okay. So I'll prove a general proof it here. So basically, we're looking at directional derivative in a direction u hat at arbitrary point, not just x naught, y naught, right? Yeah. df over ds. Now what is f? F, let's just see, it's a function of two variables, let's see, okay? Function is two variables. Now I'm going to apply the chain rule. So suppose that x is a function of s. Remember the s here, huh? What's the physical meaning of s? S basically represents the displacement, right, along the direction of a change. So I'm going to take partial derivative f over x first, then dx over ds next, and then plus partial f over partial y and dy over ds. Okay? Okay? dy over ds. So now you probably wonder, where is that from? Well, how come x is a function of s, or you'd have taken derivative s, right, with this? So let me step back a little bit here, okay? Yeah. You see, when you are walking along this direction, essentially this stickman B is walking along what? This is a, what do we call it? It's a straight line, right? It's walking a straight line. The straight line goes through which point? Here. And the straight line is parallel to which one? To this u hat. So now, would you be able to get the trajectory of the walking, or the line, or the parametric equation for this straight line? Right? So what is the parametric equation? The line equation for the stickman B. What's the line equation for stickman B? Line equation x equal to a point it passes through and times a parameter, plus a parameter times what? A parameter times, because the line is parallel to u hat, times a, right? Times a. So what parameter should we use? Usually we use a t, right? We use a t. But in this case, I'm going to use what? I'm going to use the displacement s. Okay? Right here. And the y will equal to y naught plus s times b. Okay? That's the line equation, and z equal to 0. Okay? That's in the xy plane. Okay? So, now you see, this is the trajectory of for this stickman B, okay, along the direction walking. And what we just did here, it's a partial derivative, and then there's a chain rule, dx over ds. So, guess what? The first one here, we don't know what it is, but if we have the function, we will be able to know that. But dx over ds, according to the parametric equation, this is equal to, what is that equal to? dx over ds. A, exactly. And partial f over partial y, dy over ds, which is a b, right? Just b here. Okay? So, this is the directional derivative. Okay? Just based on df over ds, that's what you get it here. And now, can you write that in a dot product format? The first one is, the second one, okay? And what's the first one? And what's the second one? U hat. So that we just proved is del f dot u hat. Okay? Yeah. So how do you calculate the directional derivative? Del f dot u hat. That's as simple as that. So basically, you need to know what direction it's going, and you are able to calculate the grading vector. That's it. Okay? Any questions? Yeah? Good. So let's do a quick exercise out here. Just to get used to this formula. I'll give you a function x e to the power y plus cosine of xy, and try to find the directional derivative of this function at point. So basically try to find this directional derivative at point 2, 0. Okay, at point 2, 0. Okay, and the u hat, the direction of walking, we don't know what a u hat is, but I'll give you this, give you a u vector. Okay, so it didn't tell you the u hat, but tells you the direction is in the direction, right, of u vector. Okay, yeah, but just one small trick at here. Right? Okay, so how do we calculate that? According to the formula, right? U hat at, so let's calculate the direction of general expression first, right? Calculate the general expression first. And that is the del f dot u hat. Okay? Del f dot u hat. So the question didn't give you the u hat, it only gave you u. So what do we have to do first? We have to normalize it, right? Yeah. Okay, normalize it. And if you normalize that, I think you end up with a pretty decent one. Okay, yeah. So now we can use this u hat for our formula. But of course, we're going to have to calculate the partial derivative, the Greeting vector first. Okay? So fx, fy dot 3 over 5, negative 4 over 5. So what's partial f over x here? I think here is the original function, right? Yeah. A little bit looks complicated, but it's not. But anyway, so we'll write into this. Okay, I'll just write it down here and see if you get this thing. Okay, so you get this. Okay, yeah. So dot product, just dot it out and expand it, and once you get it, you're getting expression. Once you get the expression, you substitute x equal to 2, y equal to 0 into the final expression, and you get the directional derivative. Okay? Yeah. So you're supposed to get df ds u hat, okay, at this 2, 0 location, you're supposed to get negative 1. Okay? Negative 1. So what does negative 1 mean? There's the decreasing, right? If you walk in this direction, 3 over 5, negative 4 over 5, there's going to be a decrease in this function here. And that value, the absolute value tells you the rate of change, basically. Okay? Okay, so here's another example, but in this example here, I don't want you to calculate, okay? I want you to look at it and kind of tell me what will be the result. What is the directional, what is the dd? Okay, what is the directional derivative, okay, of f of xy, okay, of f of xy in the direction of I hat. Okay. And how about negative I hat? Okay. So don't calculate. Just read it and think about this for a second. What would be the direction? What would be the directional derivative of this guy in this direction? I hat. So I hat is the direction walking, right? And then if I change the word a little bit, I hat is what direction? Positive x. So you're walking in the positive x direction. Is the y changing? No. So what will be the what was it? What will be the directional derivative of this function then? Exactly. Partial f over partial x. What about the second one here? Negative. Exactly. Right? So if I draw something like this, you have a surface right here, and now you're picking any point, and then you're going to walk in the positive x direction, right? So basically, along this trajectory, there is no y change. Y is not changing, right? No y change. And that's exactly basically partial f over partial x. Okay? Yeah. And this one, you work the other way, it's this. Okay? You see, right? It's all connected. So there's so directional derivative is a more general concept of slope or derivative. You can narrow that down to partial derivative. You can narrow that down to the simple slope in the scalar function case. Okay? Yeah. So the next time, if you're walking along the ramp, if somebody asks you, what is the slope of the ramp? You don't tell him what's the slope of the ramp. You have to ask me which direction you're walking first. Right? And then because, that depends on the direction you're walking, you get a different slope or directional derivative. Okay? Yeah. Okay, so before I let you go, now, then you got to think now in the next, so you walk in a different direction, you get a different slope. So which direction am I going to get the maximum slope? Which direction am I going to get basically the direction giving the maximum rate of change? Which direction? Sorry, come again? What direction? Well, U hat is the arbitrary direction. So what basically U hat you have to specify a certain direction to give you the maximum, right? What direction? The direction pointed by grading vector. So we're going to prove that in the next lecture, okay? Yeah.